Hi guys, today we'll be looking at the AM-GM inequality, or the arithmetic mean geometric mean inequality. Let's start with the optimization type problem. A rectangle has a perimeter of 32 meters. Find its maximum area. We can draw a diagram first. So this is our rectangle. It has length L, it has width W, and has a perimeter of 32 meters, meaning that L plus W is equal to 16. Well, what would be its maximum area? From our knowledge, we know that the maximum area will happen when the length is equal to the width. Why? Simply draw a few rectangles. If L is equal to 1, W equal to 15, the area is only like 15. If the length is 2, the width is 14, the area is 28. If the length is something like 4 and the width is 12, the area is only 48. And the largest occurs when the length is equal to width. And that happens when they are both equal to 8, where the area is just 8 times 8, or 64. Another way of doing this problem is using quadratics. Again, we have that L plus W is equal to 16. But this time, what we can do is we can create a function that outputs the area given a length L. So the area of a rectangle is just length times width, right? But here, we are given that L plus W is equal to 16, so width is going to be equal to 16 minus length. So the area can also be represented as L times 16 minus L. And if we were to write this in standard form, we would get f of L is equal to negative L squared plus 16L. If we were to graph this, it would look something like this. Note that this is not to scale, and this is just a rough estimate of what the graph would look like. And the x-axis is the length L, and the y-axis would be the area. So when would the area be maximized? At this vertex point, the area will be maximized because there is the highest value for the area. It is easy to find the vertex of a quadratic. For coordinate x, y of the vertex, we know that x is equal to negative b over 2a, which is negative 16 over negative 2, or 8. And then y would just be plugging x into the original function, which would yield 64, right? Because it's negative 8 squared plus 16 times 8, which is 64. And this also leads to the conclusion that the area is maximized at 64 and when the length and the width are both 8. Okay, but there's actually a third way of doing this that, in my opinion, is a lot cooler than either these two methods. And this is by using the AM-GM inequality. First of all, let's look at a brief introduction of what the AM-GM inequality is. The AM-GM inequality states that for any two positive numbers a and b, any two positive real numbers a and b, the arithmetic mean is always greater or equal to their geometric mean. What does this mean? Well, the arithmetic mean of two numbers is just taking the average of those two numbers, like how we do in daily life. So therefore, arithmetic mean is just a plus b over 2. While the geometric mean is slightly different. The geometric mean takes the product of the two numbers and then square roots it. And AM-GM states that this value, this mean, arithmetic mean, is always greater than or in some cases, equal to the geometric mean. How does this help us with our problem? Well, we know if we make a rectangle and its length and width are a and b respectively, that a plus b has to be equal to 16 from our first condition that it has a perimeter of 32. And then we want to find the maximum value of AB. Looking at this resembles very closely with our identity itself. So if a plus b is equal to 16, a plus b over 2 must be equal to 8. And then this value has to be greater than the square root of AB. Oh, wow. So this means that square root of AB has to be smaller than or equal to 8, which just directly gives us that AB is smaller than or equal to 64. So therefore, what can we say? We can say that the maximum value of AB is 64. But now a question rises. Sometimes we can say that the maximum value of AB is 64, but are we actually able to achieve this value? Well, yes, we're able to achieve this value when A is equal to B is equal to 8. When the width and length, in context of this problem, when the length and width are both 8, this yields us the area of 64, and at this time, the area is maximized. And this gives us the exact same answers as the previous two solutions. Now, let's dive a little deeper into this inequality. The first question would be, why does this inequality even work? Why does the arithmetic mean have to be greater than the geometric mean no matter what two numbers are given? Well, we can kind of explain this through algebra. This is the same as saying this. And then if we square both sides, right? Move this over. And this must be true because the square of any number has to be greater than or equal to 0. Of course, this is not a formal proof because in a formal proof, we have to start from this and then work backwards in order to yield our AM-GM inequality. So in a formal proof, we have to start by saying that a minus b squared has to be greater than or equal to 0, and then we end up with our inequality itself. But I'm not going to go too deep on that because I'm not going to talk that much about proofs right now. But a few things to notice here. The first thing is that the AM-GM inequality only works when what? When A and B are positive real numbers. When A, B are negative, there are two problems. The first thing is that it might yield complex numbers for the square root of AB. And then if both are negative, right, this may not necessarily work because the signs may mess it up. But moreover, A and B cannot be complex numbers. You cannot say for 3 plus 2i and 4 plus 6i, their sum has to be greater, the arithmetic mean of these two numbers have to be greater than the geometric mean. No. Right? This does not work at all for complex numbers. Okay? And the second thing is that when is this equal?
In other words, when does the equality case hold?
This is equal if and only if A is equal to B. Because in this case, the left-hand side is going to be A plus A over 2, and the right-hand side is going to be square root of A squared, both yielding a value of A.
Anyways, that's all for AM-GM. AM-GM basically states, to summarize, that if A and B are two real positive numbers, their arithmetic mean must always be greater than or equal to their geometric mean. And equality holds if A is equal to B, or when the two numbers are the same. In a future video, I'll be going more in depth of this concept because AM-GM also holds when there are more than two numbers. For example, when there are three numbers A, B, and C that are all real positive integers, AM-GM also holds. Their arithmetic mean still has to be greater than their geometric mean. Okay, that's all for this video. See you next time. Bye.